R is for red, O is for orange, Y is for yellow, and G is for green. B is for blue, I for indigo, and B is for violet. And that spells Roy G. Biv.
Scientists are model builders. A physical model is a copy of an object, often on a larger or a smaller scale. It is difficult to get the solar system into this classroom, but we could bring a model in. Constructing the horseshoe out of Legos is a physical model. Atomic models are different. It is not possible to directly see and simply scale up an atom. Atomic models are conceptual models. They aim to capture and describe different aspects of an atom, but they are not a literal representation. Early in this course, it was established that atoms have a dense nucleus, a lot of empty space, and electrons. Do you remember what evidence was used to support this model?
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Notice in Rutherford's nuclear model, it was not possible to directly observe the atoms. Instead, it was the deflection of the alpha particles that supported the model. Scientists have continued to learn more about atoms by considering how they absorb or emit light, or other forms of electromagnetic radiation. High-energy gamma rays may have turned Bruce Banner into the Hulk, but they're also part of a spectrometer that was included on the Mars rover to study matter on a faraway planet. You may know that X-rays are used in medical devices, but they are also used in several very important laboratory instruments to study matter. Indeed, all forms of electromagnetic radiation, ranging from high-energy gamma rays to low-energy infrared or radio waves, are used by scientists to explore and investigate matter. In this investigation, you will consider how the emission of light in the visible light region was used to support atomic models of the hydrogen atom. The purpose of the lab is to investigate the emission spectrum of hydrogen and helium gas. The emission spectrum of hydrogen will be investigated in a computer simulation. You'll find that the simulation includes different models of the hydrogen atom and also shows emission spectra consistent with each atomic model. It is okay to work with classmates and discuss the computer simulation. Be sure to ask questions. You will also experimentally analyze the emission spectra for both hydrogen and helium gas. The teaching assistant will help manage your time and direct you to the experiment, which is set up in the balance room. As described in your handout, to begin the simulation, turn on the light source. This causes white light to pass through a box of hydrogen gas. An atom of hydrogen is the question mark. Remember, this is a conceptual model. We cannot actually see the atom. The light entering the box and striking the hydrogen atom can be adjusted. You can change from white light to monochromatic light, which is just a single wavelength or color. Notice how the particles of light, or photons, change color as their wavelength changes. When a photon is emitted from an atom, its wavelength may be recorded on the spectrometer. You now should have enough information to get started on the simulation. To collect experimental data, you will use a spectroscope. As shown in these images, spectroscopes have been around for a long time. Even a modern spectroscope is little changed from one used hundreds of years ago. This instrument separates light into its component colors. One way to do this is by passing it through a prism. Consider what happens when a laser beam produces light. The light can change color as the wavelength itself changes. When the light passes through a prism, it is refracted and its direction changes. Notice how the angle of refraction changes slightly as the wavelength changes. If the light striking the prism is composed of different wavelengths, it will be separated into its component parts. The spectroscope you will be using requires calibration. The scale reading of a spectroscope shows the degree to which different colors are separated. It does not communicate the wavelength of the light, just the degree of separation. The scale readings must therefore be calibrated. This will be accomplished by correlating the measured values, the scale, with known values, the wavelengths of hydrogen's emission lines. The data from the spectroscope should be plotted with a program like Excel. Put the scale readings, what you record from the spectroscope, on the x-axis, and the known wavelengths they are matched with on the y-axis. You would determine these wavelengths in the simulation. Then add a best fit trend line. A polynomial usually works best. By using your trendline expression, a scale reading can be converted to a wavelength. This will be done for your readings from the helium emission spectrum. What is the key to this lab? Asking questions. The questions in the handout are designed to support and supplement the lecture portion of this course. Many questions are identical to those found on general chemistry exams. If you are unsure of a question or your answer, talk with classmates, the TA, etc. You are responsible for your own learning. You will earn some points for simply completing the handout. Show your work to your teaching assistant once you are done.
Stephen is a colorful man, and he proudly stands at the rain.